What if ancient civilizations possessed technology that wouldn't be reinvented for thousands of years? The standard narrative is clear. Human progress moves in one direction: forward. Ancient peoples were primitive. Their tools were simple. Their understanding limited. Then came the Industrial Revolution. Modern science. Real advancement. Except the archaeological record tells a different story. Buried in museum storage rooms are artifacts that don't fit the timeline. Devices showing mechanical sophistication that shouldn't exist for millennia. Materials requiring manufacturing processes that weren't supposed to be discovered until the modern era. These aren't fringe discoveries. These are documented finds, cataloged by respected institutions, studied by credentialed experts, then quietly shelved when the implications became uncomfortable. An ancient computer calculating astronomical positions with gear mechanisms not seen again until the 18th century. Surgical instruments requiring metallurgy that wouldn't be rediscovered for 2,000 years. Optical technology predating modern lenses by centuries. The evidence sits in archives, published in academic papers, then forgotten. Because accepting these discoveries means rewriting the entire narrative of human technological development. It means admitting ancient peoples achieved sophistication we attribute to the modern world. That challenges fundamental assumptions about progress, about civilization, about who we are and where we came from. Today, we're examining 10 ancient inventions that were thousands of years ahead of their time. Devices that modern engineers study with respect and confusion. Technology that existed, then vanished, then had to be reinvented centuries or millennia later. Each case presents physical evidence. Artifacts that exist, that can be examined, that demonstrate capabilities far beyond what the timeline allows. Fair warning: this evidence contradicts the comfortable story of constant advancement. It suggests knowledge was lost, that ancient civilizations rose to heights we're only now recovering. Some of these inventions are so sophisticated that modern recreations required computer modeling and advanced manufacturing to replicate. Yet ancient craftsmen built them with hand tools. The artifacts don't lie. They're sitting in museums right now, challenging everything we think we know about the ancient world. Question is whether we're ready to accept what they're telling us. Number 1. The Antikythera mechanism. In 1901, sponge divers discovered a shipwreck off the Greek island of Antikythera. Among the artifacts recovered was a corroded lump of bronze. Nobody paid it much attention until it split open, revealing gears inside. The Antikythera mechanism, an ancient analog computer dating to around 80 BC, the most sophisticated mechanical device known from the ancient world. Here's what makes this impossible. The mechanism contains over 30 precision bronze gears, some with triangular teeth, others with carefully calculated gear ratios, all working together to calculate astronomical positions. It predicts solar eclipses, tracks the moon's orbit, calculates the positions of known planets, even accounts for the moon's elliptical orbit using an ingenious pin and slot mechanism. That pin and slot device wasn't reinvented until the 14th century. The differential gearing wasn't seen again until the 16th century. This device shouldn't exist in 80 BC. Modern researchers have spent decades studying it. X-ray imaging revealed the internal structure. Computed tomography scans showed gear tooth profiles. Mathematical analysis decoded the astronomical calculations. The precision is staggering. Gear teeth are evenly spaced to within a fraction of a millimeter. The gear ratios are calculated to represent astronomical cycles accurately. This required understanding mathematics, astronomy, and precision metalworking, all in one device. Professor Michael Wright built a working reconstruction. He needed modern tools, computer-aided design, precision machining. Even with contemporary technology, replication was challenging. Ancient craftsmen supposedly built the original with hand tools, bronze chisels, files, manual measurement. The astronomical knowledge embedded in the device is equally impressive. It tracks the Metonic cycle, a 19-year period after which lunar phases repeat on the same calendar dates. The Saros cycle for eclipse prediction, the Callipic cycle for longer astronomical periods. This isn't basic astronomy. This is sophisticated mathematical modeling of celestial mechanics. Who built this? The device was found on a ship, probably heading to Rome. But where did it originate? Greek scientists had the astronomical knowledge, but nothing in surviving texts describes building such mechanisms. Was this unique? Or were there others that didn't survive? Ancient writers mention devices built by Archimedes, spheres that demonstrated planetary motion, mechanical models of the heavens. Those descriptions were dismissed as exaggeration or misunderstanding. The Antikythera mechanism proves they weren't exaggerating. This level of mechanical sophistication vanished with the fall of classical civilization. The knowledge was lost. For over 1,000 years, nothing comparable existed. When mechanical clocks emerged in medieval Europe, they were simpler, less sophisticated. It took centuries to match the complexity of the Antikythera mechanism. Technology regressed. Capability was lost. The mechanism sits in the National Archaeological Museum in Athens, a bronze testament to ancient engineering. Gears corroded, but still recognizable, still impossible by accepted standards. Modern engineers look at it with respect. This isn't primitive technology. This is sophisticated mechanical engineering, precision metalworking, complex mathematics. Everything necessary for an industrial revolution 2,000 years early. The Antikythera mechanism challenges the entire narrative of technological progress. It proves ancient peoples achieved sophistication we're still trying to fully understand. And it raises an uncomfortable question. What else did they build that didn't survive? Number 2. The Baghdad Battery. In 1936, German archaeologist Wilhelm König discovered strange clay jars near Baghdad, dating to around 200 BC. Parthian period. The jars weren't empty. Each contained a copper cylinder. Inside the cylinder, an iron rod. The cylinder was soldered shut with a lead-tin alloy. König recognized the configuration. These were galvanic cells, batteries. The design is simple but functional. Fill the jar with an acidic solution, vinegar or citrus juice. The dissimilar metals create an electrochemical reaction, generating approximately 1 to 2 volts. That's not much power, but it's electricity, generated intentionally. 2,000 years before Alessandro Volta supposedly invented the battery in 1800. Mainstream archaeology dismisses the battery theory. The official explanation? Storage vessels. The metal components served some other purpose, nothing to do with electricity. Except replicas work. Multiple researchers have built functioning copies. Using ancient materials and techniques, they generate measurable voltage. Engineer Willard Gray constructed a replica in 1938, connected several in series, generated enough electricity to electroplate objects, coating them with a thin layer of metal. That's significant, because some ancient artifacts show evidence of electroplating, gold-plated objects, silver coating on copper, methods that require electrical current. The conventional explanation suggests chemical gilding, applying gold leaf, or using mercury amalgams. Those methods work, but they're different from electroplating. Some ancient objects show characteristics consistent with electroplating. Even metal distribution, penetration into fine details, results difficult to achieve with chemical methods alone. If ancient peoples possessed working batteries, what did they use them for? Electroplating is one possibility. Some researchers suggest medical applications. Ancient texts describe treatments involving tingling sensations. Could these be electrical therapy? Others propose religious purposes. Batteries hidden in religious artifacts, creating mysterious sensations when priests touch them, demonstrating divine power through early electrical technology. The evidence remains circumstantial. We have jars that function as batteries. We have ancient objects that might be electroplated. We have gaps in the historical record about ancient manufacturing techniques. What we don't have is clear documentation that ancient peoples understood electricity as we do. But absence of documentation doesn't mean absence of knowledge. Most ancient technical knowledge was transmitted through apprenticeship. master craftsmen teaching students, trade secrets closely guarded. When civilizations collapsed, specialized knowledge disappeared. The craftsmen died, the workshops burned, the secrets were lost. The Baghdad batteries might represent exactly that. Practical electrical technology used for specific applications, knowledge held by specialists, lost when the Parthian civilization fell. Modern electrical theory wasn't necessary to discover batteries' work. Trial and error with different metals and solutions could reveal the effect. Ancient metalworkers had extensive practical experience. They might have stumbled onto galvanic cells without understanding the physics, then found uses for the electrical current generated. The batteries exist. They're in museums. The Smithsonian has examples. The National Museum of Iraq had more before the looting in 2003. They're real artifacts. Their function as batteries is demonstrable. Whether ancient peoples actually used them that way remains debated. But the possibility exists. That ancient technology included functional electrical devices. 2 millennia before the Industrial Revolution supposedly brought electrical power to humanity. The Baghdad batteries sit in storage. Simple clay jars with metal components, capable of generating electricity using 2,000-year-old technology. Evidence that ancient innovation sometimes reached destinations we assume are modern. Number 3. The Damascus steel secret. For centuries, Damascus steel was legendary. Swords forged from this material were sharper than European blades, more flexible, nearly unbreakable. They could reportedly cut through lesser swords. The steel had distinctive wavy patterns on the blade surface, beautiful and functional. The patterns indicated the internal structure, carbon nanotubes and cementite nanowires, creating exceptional properties. Yes, carbon nanotubes. In medieval steel, Damascus steel production began around 300 AD in India. The technique spread to the Middle East. Syrian bladesmiths in Damascus perfected the craft, hence the name. Then, around 1700 AD, the technique was lost completely. Bladesmiths forgot how to make it. The knowledge vanished. For 300 years, metallurgists tried to recreate Damascus steel. They failed. The closest approximations didn't match the original properties. Something about the ancient technique remained elusive. In 2006, researchers finally understood why. Electron microscopy revealed carbon nanotubes in ancient Damascus steel, structures 1 to 7 nanometers in diameter. Modern materials science didn't discover carbon nanotubes until 1991. Yet they existed in steel made over 1,000 years ago. How? Ancient bladesmiths didn't know about nanotubes. They didn't have electron microscopes. They couldn't see molecular structures, but they knew the process. Specific iron ore from India contained trace elements: vanadium, chromium, manganese, rare earth elements. When smelted under exact conditions, these elements catalyzed nanotube formation. The swordsmiths didn't understand the chemistry, but they knew the recipe. Use this ore, smelt at this temperature, forge this way, cool like this. The result was steel with mechanical properties that wouldn't be achieved again until modern metallurgy. Professor Jeffrey Wadsworth from Stanford studied Damascus steel extensively. His analysis showed the ancient material had properties matching modern high-carbon steel, but created using pre-industrial techniques. The secret lay in the process: repeated heating and folding, specific temperature ranges, controlled cooling, all done by craftsmen judging by color and feel. No thermometers, no precise measurements. Yet they achieved molecular structures modern metallurgists create intentionally with computer-controlled furnaces. When the Indian ore mines were exhausted, Damascus steel production ceased. Bladesmiths tried using other iron sources. The results weren't the same. Without the specific trace elements, nanotubes didn't form. The knowledge was process-dependent, tied to specific materials. When those materials became unavailable, the technique failed. Eventually, it was abandoned and forgotten. Modern recreations of Damascus steel require understanding the nanoscale structures, using electron microscopy to verify nanotube formation, controlling furnace atmospheres precisely, Ancient bladesmiths achieved the same results through empirical knowledge, generations of refinement, trial and error, mastery of craft. But the result was nanotechnology. 1,000 years before modern science discovered it existed, Damascus swords exist in museums worldwide. The Metropolitan Museum of Art has examples. The Wallace Collection in London, the Smithsonian, private collections. They're real. The nanotubes are verifiable. Electron microscopy confirms their presence. Ancient technology created materials science wouldn't understand for a millennium. The swords themselves are evidence. Physical proof that ancient metallurgy achieved sophistication modern science assumed was impossible. The technique was lost not through lack of documentation. The secret was in the materials and process. When the ore source disappeared, the technique couldn't be replicated elsewhere. Knowledge tied to specific natural resources. When those resources were exhausted, the knowledge became useless, eventually forgotten. Damascus steel proves ancient technology sometimes exceeded what later civilizations could achieve. Progress isn't always forward. Sometimes it's circular, reaching heights, then falling, then climbing again. The swords remain, sharp after centuries, still demonstrating properties that required rediscovering nanotechnology to explain. Number 4. Roman concrete. The Pantheon in Rome has stood for nearly 2,000 years. Its massive concrete dome remains the largest unreinforced concrete dome in the world. No cracks, no significant deterioration. Modern concrete structures start crumbling after 50 years. Bridges need replacement. Buildings require reinforcement. Concrete has a limited lifespan. Roman concrete lasts millennia. In seawater, it actually gets stronger over time. How? For centuries, nobody knew. The recipe was lost when the Roman Empire fell. Medieval builders couldn't replicate it. They used different materials, inferior results. Recent analysis revealed the secret. Roman concrete used volcanic ash, specifically from Pozzuoli near Naples. Mixed with lime and seawater, the chemical reaction created aluminum tobermorite crystals. These crystals form over time, filling microcracks, making the concrete stronger as it ages. The opposite of modern concrete, that weakens through crack propagation. In seawater, the effect is enhanced. Saltwater reacts with the volcanic ash, precipitating additional crystals. Ancient Roman harbor structures are more solid now than when first built. Modern concrete uses Portland cement, invented in 1824. It's strong initially, but it deteriorates. Water infiltration causes steel reinforcement to rust. Expansion cracks the concrete. Roman concrete contained no steel reinforcement. The material itself provided all structural strength, and it improved with age. The Pantheon's dome is pure Roman concrete, coffered to reduce weight, graduating from heavy aggregate at the base to lightweight pumice at the top. Brilliant engineering maximizing material properties. Engineers studying it calculate that building an equivalent structure today would be extremely difficult. Modern concrete couldn't span that distance unreinforced. Steel reinforcement would be necessary, changing the entire structural approach. The Romans built it 2,000 years ago. It's still standing, still functional, still the largest unreinforced concrete dome ever constructed. Harbor installations at Caesarea and other Roman ports remain intact, submerged for centuries, growing stronger instead of eroding. Modern harbor construction requires replacement every few decades. Roman concrete endures. Why was this lost? The fall of the Roman Empire disrupted trade networks. Pozzolanic ash from specific sources became unavailable. Local builders used whatever materials were at hand. The results weren't comparable. Over generations, the original techniques were forgotten. Medieval and Renaissance builders developed their own methods, different chemistry, different properties. It wasn't until modern materials science could analyze ancient samples that the Roman recipe was understood. Researchers examined cores drilled from ancient structures. Electron microscopy revealed the crystal structures. Chemical analysis identified the volcanic ash composition. Now we know how they did it. But replicating it requires specific volcanic ash. the exact type used by Romans. Modern concrete manufacturing uses different approaches: industrial processes, standardized materials. Returning to Roman methods would require changing the entire concrete industry, sourcing volcanic ash, adjusting mixture ratios, accepting longer curing times. The economic incentives don't exist. Modern concrete is cheaper to produce, even if it doesn't last as long. So Roman concrete remains superior. 2,000 years after it was developed, the Pantheon stands as proof. Harbor installations demonstrate longevity modern materials can't match. Ancient technology surpassing modern equivalents. Not through complexity, through better understanding of natural materials and their properties. The Romans didn't have chemistry textbooks. They didn't understand crystal structures or chemical bonds. But they knew what worked. They refined the technique. They built structures that outlasted their civilization, and were still trying to match their achievement. Roman concrete is evidence. Physical evidence. Buildings and structures existing right now, demonstrating material properties modern engineering struggles to replicate. The recipe was lost for 1,500 years. We're only now understanding how it worked, and acknowledging that sometimes ancient solutions were simply better. Progress isn't always forward. Sometimes it's rediscovering what was forgotten. Number 5. The Greek fire mystery. Byzantine Empire. 7th century AD. Arab fleets threatened Constantinople. The city faced invasion by sea. Then Byzantine defenders deployed a weapon that changed naval warfare. Greek fire. A liquid that burned on water. That couldn't be extinguished by conventional means. That adhered to surfaces and continued burning. Terror weapon that destroyed enemy fleets. The formula was classified as a state secret. Only the emperor and the craftsmen who made it knew the recipe. Production was controlled. Knowledge was guarded. It worked. Arab invasions were repelled. The Byzantine navy dominated the Mediterranean for centuries. Greek fire was the decisive advantage. Then the Byzantine Empire fell. 1,500 years ago. The secret died with it. Nobody today knows exactly what Greek fire was. We know what it did. Accounts describe its effects. But the precise composition remains unknown. Modern attempts to recreate it produce approximations. Napalm-like substances, but not exact matches. Something about the ancient formula remains elusive. Historical accounts describe Greek fire's properties. It burned on water. Water didn't extinguish it. Some accounts suggest water made it burn more intensely. It was projected through siphons. Bronze tubes mounted on ships. The substance shot out, ignited, engulfed enemy vessels in inextinguishable flames. What chemical composition produces these effects? Modern analysis suggests a mixture. Petroleum distillates, possibly naphtha, sulfur, quicklime, saltpeter maybe. But the exact ratios and preparation method? Unknown. The quicklime component is interesting. Quicklime reacts violently with water, producing intense heat. That would explain why water intensified the flames. But mixing quicklime with flammable liquids is dangerous. Requires careful handling. Byzantine chemists managed it, created a weapon that remained effective for centuries. Then the knowledge vanished. Why such secrecy? State security. Greek fire gave Byzantium a decisive military advantage. Revealing the formula meant losing that advantage. Enemies could produce it themselves. So production was restricted. Knowledge tightly controlled. Only certain families manufactured it. Under imperial supervision, with heavy penalties for disclosure. That secrecy preserved the advantage. But it also meant when those families died out, when the empire collapsed, the secret disappeared completely. No written formulas survived. Any documentation was destroyed or lost. The craftsmen took the knowledge to their graves. Modern militaries have incendiary weapons. Napalm, white phosphorus, thermite. All effective. But they're not Greek fire. The ancient weapon had specific properties modern equivalents don't precisely match. The terror factor was significant. Enemy sailors faced flames that couldn't be escaped. Water offered no safety. Jumping overboard meant burning on the surface. Ships couldn't run. The flames pursued them. psychological warfare as much as physical destruction, Greek fire demonstrates something important about ancient technology. When survival depends on innovation, solutions emerge. The Byzantines faced existential threat. They developed a superweapon. It worked for centuries. Then the knowledge was lost because it was too secret, controlled too tightly. When the control system collapsed, the knowledge died. We have Byzantine accounts describing Greek fire, military manuals mentioning it, historical chronicles documenting battles where it was used, but no recipe, no chemical formula, no production instructions. The weapon existed, hundreds of years of documented use, physical evidence in archaeological remains, burned ship timbers showing unusual residue patterns. But we can't recreate it exactly. Despite modern chemistry, despite sophisticated analysis, something about the ancient formula remains mysterious. Greek fire represents ancient chemical engineering, weapons development, industrial secrets, all existing in the medieval period, then vanishing completely. A reminder that sometimes knowledge is held so tightly it dies with the holders. That secrecy, while protecting advantages, also ensures those advantages can be lost forever. The Byzantines saved their empire with Greek fire, then lost the formula that saved them. The weapon became legend. Its composition became mystery. Evidence that ancient peoples developed technology we still struggle to fully understand or replicate, even when we know what it did. Number 6. The Lycurgus Cup. In the British Museum sits a Roman cup dating to the 4th century AD. The Lycurgus Cup, carved from dichroic glass, beautiful craftsmanship, depicting the death of King Lycurgus. But the real mystery is the glass itself. In normal light, the cup appears green. Shine light through it, and it turns red, deep ruby red. The color change is dramatic. Complete transformation. This is dichroic glass. The optical properties depend on how light interacts with the material. Modern dichroic glass uses thin film coatings, layers of metallic oxides deposited under vacuum. High-tech manufacturing. The Lycurgus cup was made in the 4th century. No vacuum chambers, no thin film deposition equipment, no modern optical engineering. Yet it works perfectly. The color change is vivid. The optical properties are precisely controlled. In 1990, researchers analyzed the glass composition. They discovered something extraordinary. The glass contains gold and silver nanoparticles, particles about 70 nanometers in diameter, suspended throughout the matrix. These nanoparticles create the dichroic effect. When light hits them, they resonate at specific frequencies. Green light scatters, red light transmits. The result is the color change. This is plasmonics, advanced nanotechnology. The same principles used in modern optical sensors and medical diagnostics. In a Roman cup from 1500 years ago, how did Roman glassmakers achieve this? They didn't understand plasmonics. They didn't have electron microscopes to see nanoparticles. They couldn't consciously engineer optical properties at the nanoscale. But they knew a process. Add certain materials to the glass, melt gold, silver, other metals, control the temperatures, cool in specific ways. The result was dichroic glass. They couldn't explain why it worked, but they could reproduce the effect. That's masterful, empirical craftsmanship. Modern attempts to recreate Roman dichroic glass have struggled. The particle size must be precise. Too large, and the optical effect disappears. Too small, and the colors change. The distribution must be even throughout the glass. Achieving this with medieval furnaces and no analytical instruments seems impossible. Yet the cup exists. The nanoparticles are there, documented by transmission electron microscopy. Professor Ian Freestone from University College London studied the cup extensively. His conclusion? The Romans achieved accidental nanotechnology. They didn't plan it, but through experimentation, they discovered techniques that created nanostructures. The Lycurgus cup might be unique. Only one example is known to survive. Were there others? Probably. But dichroic glass was rare, difficult to produce, expensive, only for elite patrons. Most examples didn't survive. Broken, lost, melted down for the gold and silver content. The Lycurgus cup survived because it was treasured, protected, eventually acquired by the Rothschild family, then donated to the British Museum. It sits in a display case, lights illuminating it from different angles, demonstrating the color change, green to red, red to green. A light show created by Roman nanotechnology. Visitors walk past amazed. Few understand they're seeing evidence of ancient optical engineering that wouldn't be intentionally recreated for 1,500 years. The cup is real. The nanoparticles are verified. The optical properties are demonstrable. Evidence that ancient craftsmen, through empirical methods and master craftsmanship, achieved results that modern science requires sophisticated technology to replicate. They didn't understand the physics, but they didn't need to. They knew what worked. They perfected the technique. They created objects that still baffle researchers today. The Lycurgus cup challenges assumptions about technological progress. Nanotechnology isn't purely modern. Ancient peoples accessed it through different methods, empirical rather than theoretical, but they reached the same destination. The cup remains. Physical proof sitting in London, anyone can visit. See the color change. Witness Roman nanotechnology in action. Evidence that ancient innovation sometimes exceeded anything that followed for over a millennium. Number 7. The Nimrud lens. In the ruins of the Assyrian palace at Nimrud, archaeologist Austin Henry Layard discovered something unexpected. 1850. A piece of polished rock crystal. Convex shape, ground and polished with precision. The Nimrud lens. Dating to around 700 BC. 2,700 years old. It's an optical lens, shaped correctly to magnify or focus light. The grinding is precise. The curve is regular. The polish is excellent. Optical lenses weren't supposed to exist until the 13th century. Spectacles appeared in Italy around 1275. That's when lens grinding supposedly began in earnest. The Nimrud lens is 600 years earlier, in Mesopotamia, in the Assyrian Empire. Conventional archaeology calls it a decorative item, perhaps a piece of furniture inlay, maybe a magnifying glass for starting fires. Nothing sophisticated. Except optical analysis reveals something else. Professor Giovanni Pettinato examined it in 1998. His conclusion? It's a functioning lens. The optical properties are consistent with deliberate design. When tested, the lens produces magnification of about 3 times, enough to assist detailed work, engraving, jewelry making, reading small text. Ancient Assyrian craftsmen produced incredibly detailed work. Cylinder seals with microscopic engravings, jewelry with fine details, palace reliefs with precise inscriptions. How did they see these details without magnification? Official archaeology says keen eyesight and good lighting. But the lens exists, found in the same context as the detailed work. Coincidence? Or tool of the trade? Other ancient lenses exist. A Roman lens was found in Bulgaria, dating to the 1st century AD. Multiple examples from ancient Egypt. Polished quartz or crystal, shaped to magnify. These aren't isolated artifacts. They're a pattern, suggesting ancient peoples understood basic optics, used lenses for practical purposes. Why isn't this accepted? Because it complicates the narrative. Optics is supposed to develop in medieval Europe. Islamic scholars, Italian craftsmen, the scientific revolution. Ancient Mesopotamia isn't supposed to have optical technology. That's too advanced, too early. But the lens exists. It works. The optical properties are measurable. David Brewster, a 19th century physicist, examined ancient lenses. His conclusion? They show understanding of refraction and focal length, deliberately ground to specific curves, not accidental products. Modern lens grinding requires precision equipment, calibrated grinding wheels, polishing compounds, quality control. The ancient process was manual, using abrasives, probably sand, patience and skill. Creating a precision lens by hand is difficult. Maintaining the correct curve, achieving even polish, removing imperfections, it takes expertise, understanding, practice. Assyrian craftsmen possess that expertise. The lens proves it. What did they use lenses for? Magnification for detailed work is the obvious application. But some researchers suggest astronomical uses. Lenses can focus light. Ancient astronomers tracked celestial movements, documented eclipses, calculated planetary positions. Could they have used lenses to see celestial objects more clearly? No evidence proves this, but the possibility exists. Ancient astronomy was sophisticated. Adding optics would enhance capabilities. The Nimrud lens sits in the British Museum, available for examination. Researchers have studied it, photographed it, measured its optical properties. It's real. It's ancient. It works as a lens, evidence that optical technology existed far earlier than the accepted timeline, that ancient peoples understood refraction, used lenses practically. The lens challenges assumptions, forces reconsideration of ancient capabilities, suggests technologies we attribute to medieval or modern periods have older roots. Knowledge was lost, techniques forgotten. The lenses survived as curiosities, their original purpose misunderstood or dismissed, until modern analysis revealed what they really were: functional optical instruments. Ancient technology predating the accepted invention of lenses by centuries. The Nimrud lens is evidence, physical evidence, demonstrable optical properties, ancient craftsmanship achieving precision that required rediscovering optical science to fully appreciate. Another example of ancient innovation reaching beyond accepted limitations, of knowledge existing, then vanishing, then being rediscovered centuries later. The lens remains, 2,700 years old, still capable of magnification, still challenging the narrative of technological progress. Number 8. The Delhi Iron Pillar. In Delhi, India stands an iron pillar, 7 meters tall, weighing over 6 tons, dating to around 400 AD, 1,600 years old. It doesn't rust. Iron oxidizes. Exposed to air and moisture, iron develops rust, red iron oxide that flakes and spreads. Modern iron structures require maintenance, paint, protective coatings, constant vigilance against corrosion. The Delhi pillar stands outdoors, exposed to monsoon rains, humid conditions. For 16 centuries, no rust. Tiny spots of surface corrosion appear, but no deep rusting, no structural degradation. The pillar remains solid, sound. After 1,600 years of weathering, how? Modern metallurgy struggled to explain this. Iron shouldn't behave this way. Something about the Delhi pillar's composition must be special. Analysis revealed the secret. The iron contains high phosphorus content, about 1%. When exposed to moisture, this phosphorus creates a thin protective film, misawanite, an iron-phosphorus-oxygen compound that seals the surface. This film prevents deeper corrosion. It's self-renewing. If scratched, new film forms. The pillar protects itself through its metallurgical composition. Creating this required sophisticated understanding. Ancient Indian metallurgists selected specific iron ores, smelted under controlled conditions. The phosphorus content wasn't accidental. It was intentional. They didn't understand the chemistry, no atomic theory, no knowledge of phosphorus compounds, but they knew the process. This ore, this temperature, this technique. The result was corrosion-resistant iron. Modern rust-resistant alloys use chromium, stainless steel. Developed in the early 20th century, the Delhi pillar achieved similar results with phosphorus, 1,500 years earlier. The pillar was originally part of a Hindu temple, later moved to its current location. It bears inscriptions in Sanskrit, praising King Chandragupta II, documenting his reign and achievements. The inscriptions remain legible. After 16 centuries, because the surface hasn't corroded away, the text is preserved by the same protective mechanism that preserves the entire pillar. Metallurgist Robert Hadfield studied the pillar in 1912. He marveled at the iron quality. His analysis showed it was essentially pure, very low carbon content, high phosphorus, exceptional manufacturing. Creating iron this pure requires careful smelting, controlling furnace conditions, removing impurities, all achieved with medieval technology. Charcoal furnaces, manual operation, no temperature gauges. Ancient metallurgists judged by experience. Color of the metal, behavior during forging, sound when hammered, empirical knowledge refined over generations. The result was iron superior to much of what medieval Europe produced, corrosion resistant, pure, well manufactured. The pillar isn't unique in principle. Other ancient Indian iron objects show similar properties. The famous Ashoka pillars, various iron beams in temples, all exhibit resistance to corrosion. But the Delhi pillar is the most impressive, most visible, standing in public, demonstrating ancient metallurgical achievement for everyone to see. Modern attempts to recreate it face challenges. The phosphorus content must be precise. Too much, and the iron becomes brittle. Too little, and the protective film doesn't form properly. Getting the balance right requires understanding the chemistry. Ancient metallurgists achieved it through empirical methods, trial and error, observation, refinement of technique. The pillar stands as testimony. Indian metallurgy, in the first millennium AD, achieved sophistication Western metallurgy wouldn't match for over 1,000 years. It's evidence, physical evidence, standing in Delhi right now. Anyone can visit, touch it, see the lack of rust, witness ancient technology in action. The pillar challenges assumptions, forces recognition that ancient civilizations developed technologies independently, achieved results through different methods, reached destinations Western science assumes are modern inventions. India had advanced metallurgy, sophisticated understanding of materials, techniques that produced results. We now require chemistry and materials science to explain. The Delhi pillar proves it. 1,600 years of exposure, no significant rust, still standing, still demonstrating that ancient knowledge sometimes exceeded what followed for centuries. Evidence that technological progress isn't linear, isn't Western, isn't modern. Ancient peoples across different cultures achieved sophistication that disappeared and had to be rediscovered. The pillar remains. Iron that doesn't rust. Ancient metallurgy that modern science studies with respect. Technology from 1,600 years ago that still works perfectly. Number 9. The Archimedes screw. 3rd century BC. Greek mathematician Archimedes supposedly invented a device for raising water, a helical screw inside a cylinder. Rotate it, and water climbs upward against gravity. Simple principle. Revolutionary impact. The Archimedes screw became fundamental to hydraulic engineering, used for irrigation, drainage, water supply. Still in use today. Modern wastewater treatment plants use Archimedes screws 2,300 years later. Still the best solution for certain applications, except Archimedes probably didn't invent it. Recent discoveries suggest the device existed earlier. Assyrian palace reliefs from 7th century BC show screw-like devices in irrigation systems. Egyptian tomb paintings depict similar mechanisms. Dating to well before Archimedes lived. The device might be much older. The principle might have been discovered independently multiple times. But Archimedes refined it, analyzed it mathematically. His writings describe the geometry, the optimal angles, the efficiency calculations. He turned practical technology into engineering science. The screw's efficiency is remarkable. It can lift water several meters with minimal energy input. Manual operation suffices. One person turning a handle can move significant volumes of water. Modern pumps are more powerful, but they require energy, electricity or fuel, maintenance, complexity. The Archimedes screw works with human power. No fuel needed, minimal maintenance, simple construction. For low-tech applications, it remains optimal. Developing nations still use Archimedes screws for irrigation because they work, because local craftsmen can build them, because they don't break down easily. Ancient technology still serving modern needs, because sometimes simple solutions are best. The principle extends beyond water lifting. Screw mechanisms appear in various applications: conveyor systems, grain elevators, pasta makers, ship propellers are underwater Archimedes screws, generating thrust by moving water, all based on technology perfected 2,300 years ago. What makes this significant? Ancient engineers understood mechanical advantage, leverage, efficiency. They could analyze systems, optimize designs, create solutions that remain relevant today. Archimedes' writings on the screw demonstrate mathematical sophistication. He calculated the optimal pitch angle, the relationship between rotation speed and water flow, the forces involved. This is engineering analysis, mathematical modeling, optimization, everything necessary for modern engineering. In the 3rd century BC, ancient Greece produced remarkable thinkers: Archimedes, Euclid, Pythagoras. Their mathematics and science remained foundational for 2,000 years, only surpassed when modern science built upon their work. But much was lost. When the Library of Alexandria burned, countless texts disappeared. Scientific knowledge, engineering designs, mathematical treatises, gone. What survived came through Arabic translations, medieval copies, fragments preserved by chance. Most of ancient engineering knowledge vanished. The Archimedes screw survived because it was too useful to forget, too practical to abandon. People kept building them because they worked. The device itself preserved the knowledge. Modern analysis of the screw reveals sophisticated understanding. The helical surface creates optimal water lifting. The angle balances efficiency against practical construction. The design shows deep understanding of fluid dynamics and mechanics. Archimedes didn't have calculus, no modern physics textbooks, no computer modeling, but he understood the principles, applied mathematical reasoning, created optimal design through pure thought and observation. The screw demonstrates something important. Ancient peoples weren't primitive. They were intelligent, creative, capable of sophisticated analysis. They lacked our tools, our accumulated knowledge, our technology, but they had the same mental capacity, same problem-solving ability. Given that, they achieved remarkable things. The Archimedes screw is just one example. A device so well designed that 23 centuries later, we still use it, still recognize it as the best solution for certain applications. Modern engineering refined it. Metal construction instead of wood, precise manufacturing instead of handcrafting. But the fundamental principle remains unchanged. The Archimedes screw is evidence. Evidence that ancient engineering achieved lasting solutions, that ancient analysis produced optimal designs, that ancient technology sometimes reached conclusions that remain valid today. The device works, still works, after more than 2 millennia, still being installed in modern facilities, still the preferred solution when conditions suit it. Ancient technology serving modern needs, because good engineering is timeless, because optimal solutions don't become obsolete, because sometimes ancient inventors got it exactly right. Number 10. The Hufeng Seismoscope. Year 132 AD. Han Dynasty, China. Astronomer and inventor Zhang Heng presents a device to the imperial court, the world's first seismoscope, an instrument that detects distant earthquakes. 8 dragon heads arranged around a bronze vessel. Each dragon holds a bronze ball in its mouth. Below each dragon sits a bronze toad with open mouth. When an earthquake occurs, one ball drops, falls into the toad's mouth. The direction indicates where the earthquake originated. The device detects seismic waves, determines direction, announces the event with a mechanical signal. This is 1,800 years before modern seismographs. Historical records document the device working. In year 138, a ball dropped. No earthquake was felt in the capital. Officials dismissed it as malfunction. Days later, messengers arrived. An earthquake had struck 400 miles west, exactly the direction the device indicated. The court was astounded. The device worked. It detected earthquakes too distant to feel, indicated direction accurately, demonstrated scientific instrumentation far ahead of its time. How did it work? The original device didn't survive. Only descriptions in historical texts. Chinese engineers have attempted reconstructions. The principle appears to be a pendulum mechanism. An earthquake generates seismic waves. These waves cause the pendulum to swing. The motion triggers a mechanism, releases the ball in the appropriate direction. Simple principle, sophisticated execution. Creating a mechanism sensitive enough to detect distant earthquakes, but stable enough to avoid false triggers, requires precision. The pendulum must be carefully balanced. The release mechanism must be reliable. The whole system must work consistently. Zhang Heng achieved this in the 2nd century, using bronze casting, mechanical linkages. No electricity, no electronics, pure mechanical engineering. Modern seismographs weren't developed until the 19th century. European scientists created instruments to record earthquake intensity and timing, but these required advances in precision manufacturing, recording methods, materials science. Zhang Heng's device was 1300 years earlier. Different approach, mechanical rather than recording, but functionally similar. Detecting seismic activity, indicating direction. Chinese science in the Han Dynasty was remarkably advanced. Zhang Heng also built an armillary sphere, a mechanical representation of the heavens, water-powered, demonstrating planetary motion, calculating astronomical positions. His scientific instruments demonstrated sophisticated understanding. Mathematics, mechanics, astronomy, all integrated into functional devices. Much of this knowledge was lost. The Hufeng seismoscope wasn't replicated after Zhang Heng's death. The technology was forgotten. China faced invasions, political upheaval, scientific traditions were disrupted. When European visitors arrived in later centuries, they found no trace of Zhang Heng's seismoscope. The device existed only in historical records. Many Western scholars dismissed these records as exaggeration or myth, until modern researchers reconstructed the device. Following the historical descriptions, testing different mechanical approaches, eventually creating working replicas that demonstrate the principal functions. The device could work. The description was accurate. Zhang Heng really did create a functional seismoscope 1800 years ago. Why does this matter? It demonstrates ancient Chinese science achieved sophistication Western history often overlooks. China had scientific traditions, technological innovation, engineering capabilities. These weren't primitive, they were advanced, different from Western approaches, but reaching similar levels of sophistication. The Hufeng seismoscope represents ancient instrumentation, scientific devices for observing natural phenomena, mechanical engineering applied to investigation, everything necessary for scientific method. 1800 years ago, in Han Dynasty China, modern science assumes the scientific revolution began in Renaissance Europe. That systematic observation and instrumentation started with Galileo and his contemporaries. But Zhang Heng was doing similar work 1300 years earlier, creating instruments, making observations, recording phenomena, analyzing results. The seismoscope is evidence. Historical documentation exists. Reconstruction proves the principle works. Ancient Chinese science achieved instrumentation that wouldn't appear in Europe for over a millennium. Knowledge developed independently. Different cultures reaching similar conclusions through different paths. Ancient innovation occurring globally, not confined to one region or civilization. Zhang Heng's seismoscope challenges Eurocentric narratives, forces recognition that scientific sophistication emerged in multiple locations, that ancient peoples worldwide developed technology and science. The device represents that global innovation, Chinese engineering, scientific instrumentation, mechanical sophistication, all existing in the 2nd century, all forgotten or dismissed, all now recognized as genuine achievements that predate European equivalents by over 1,000 years. The Hufeng seismoscope demonstrates what this entire investigation reveals. Ancient technology was sophisticated. Ancient peoples were innovative. Ancient knowledge reached levels that sometimes exceeded what followed for centuries. Progress isn't linear. knowledge gets lost, civilizations fall, technologies are forgotten, then rediscovered later, often by different cultures. The seismoscope proves it. 1800 years old, functional, demonstrating ancient Chinese engineering that modern science studies with respect. 10 ancient inventions. 10 technologies that were centuries or millennia ahead of their time. From the Antikythera mechanism's precision gears predicting eclipses, to Zhang Heng's seismoscope detecting distant earthquakes. From Roman concrete that lasts thousands of years, to Damascus steel containing medieval nanotechnology, the pattern is undeniable. Ancient peoples achieved technological sophistication far beyond what standard history acknowledges. These aren't myths. These aren't legends. These are physical artifacts, sitting in museums, available for examination, demonstrating capabilities that modern science struggles to explain or replicate. The Lycurgus cup contains nanoparticles, creating optical effects. The Baghdad batteries generate electricity. The Nimrud lens focuses light with precision grinding. The Delhi pillar resists corrosion through metallurgical sophistication. All ancient, all verifiable, all challenging the narrative of constant technological progress. What does this mean? It means human capability isn't limited to modern times. Ancient peoples were intelligent, creative, innovative. They lacked our accumulated knowledge, but they didn't lack mental capacity or problem-solving ability. Given that, they achieved remarkable things, developed technologies through empirical methods, created solutions that remained optimal for centuries or millennia. Much of this knowledge was lost. Civilizations collapsed, libraries burned, trade networks disrupted, specialized knowledge held by craftsmen died with them. The technologies survived as artifacts, mechanisms whose purpose was forgotten, materials whose composition remained mysterious, devices that worked without anyone remembering how they were made. Only modern analysis revealed what they represented: ancient sophistication, lost knowledge, technology ahead of its time. This challenges fundamental assumptions about progress, about civilization, about human development. The standard narrative says technology advances linearly, ancient to medieval to modern, each era surpassing the last. But the evidence says otherwise. Ancient peoples sometimes achieved heights that later civilizations couldn't match, technology that had to be reinvented centuries later, solutions that remain optimal today. Progress isn't linear. It's cyclical, climbing, falling, climbing again. Knowledge is gained, knowledge is lost, knowledge is rediscovered. The artifacts prove it. Ancient computers, calculating astronomical cycles. Medieval steel, containing nanotechnology. Roman materials, outperforming modern equivalents. Evidence that ancient innovation reached destinations we assume are modern. That knowledge existed, vanished, required rediscovery. Why does mainstream history resist acknowledging this? Because it complicates comfortable narratives. Because it requires admitting ancient peoples achieved sophistication we've only recently recovered. Because it suggests Western civilization isn't the unique source of human advancement. The evidence exists regardless, in museums, in archaeological sites, in surviving structures that demonstrate ancient capabilities. The Pantheon stands. Damascus swords remain sharp. The Antikythera mechanism's gears still interlock with precision. The Delhi pillar doesn't rust. Physical evidence. Documented, measured, analyzed, proving ancient technology sometimes exceeded anything that followed for centuries. What else was lost? What other knowledge vanished when civilizations fell? What capabilities did ancient peoples possess that we're still trying to rediscover? The 10 cases examined here represent what survived. Fragments that made it through history. Most ancient technology didn't survive. Most knowledge was lost. These survivors hint at what existed, suggest that ancient innovation was more sophisticated than accepted history allows, prove that human capability has always been remarkable given the right conditions. The evidence has been presented. The artifacts exist. The technology is verifiable. What we believe about ancient peoples is a choice. But the devices don't care what we believe. They keep demonstrating ancient sophistication, keep challenging assumptions, keep proving that sometimes ancient inventors got there first, and sometimes got it better than anything that followed. Human innovation is timeless. The capacity for discovery isn't modern. Ancient peoples looked at their world, saw problems, created solutions. Some of those solutions were so good, they're still optimal today. That's not primitive. That's sophisticated. That's evidence of human capability spanning millennia, proving that intelligence, creativity, and innovation have always been part of who we are. The ancient inventions demonstrate it. The lost technologies prove it. The artifacts that challenge our assumptions confirm it. Ancient peoples were remarkable. Their achievements deserve recognition. Their knowledge deserves respect. Their innovations deserve acknowledgement as genuine contributions to human technological development. The evidence speaks. Clearly, undeniably, from artifacts sitting in museums right now, maybe it's time we started listening.